So what I'm going to present today, it's about the joint in FRB composite structure. And for those of you who are civil engineering, know that composite material are being used in civil engineering recently. But since they are new, we don't have many experience with this material. And maybe the problem seems simple, but when we want to design a joint, we see that it's really complicated. For example, here it's a building in Switzerland that made of GFRP profile, and then the profile are made from GFRP laminate or GFRP profile that connected together with adhesive layer. And in the frame they are connected with the bolted. So here actually present two different type of joint. One is bolted and one is the adhesive bond. But my presentation is mainly on the adhesive joint. Another type of adhesive joint is when we have two profile like this and we use it for the deck in the bridges. So here we have the adhesive bond, and also when we want to put the deck on the girder, also there is adhesive bond here. And this has been tested, for example, to know the behavior, because there is no standard or no criteria to design it. So what we do, we test it and then we verify the result. And we have seen that the failure was in the joint here and also in this part. So in general, if we have a joint and we want to see how it failed, for example, if it's a double lap joint, that here there is one side that we have pull it in this direction and then it goes on these two directions. So a crack initiate here and then the crack propagate. If we plot the energies release rate for mode 1 and mode 2, you can see first of all it's a mixed mode. There is no pure mode, it's always mixed mode. And also the ratio between these two modes is changing. So when we tackle this problem, actually we do some tests to find out the failure criteria for fixed mixed mode and also for pure mode 1 and pure mode 2. And then depending on the material characteristic, this can be a linear or convex or concave failure criteria. So the material that I have studied, it's actually a fiber composite. So here it's a section of the material. These dots are the fiber that goes in through the direction, and these are the fiber that are in the plane, and those white points are the matrix between the fibers. So the width is 40 millimeter, the thickness is 6 millimeter. So this is actually half of a cross section is about 3 millimeter, and the tensile strength was about 300 MPa, and the longitudinal Young modulus 25 GPa. Then we have two of these two laminate to glue them together to build the joint. So the adhesive that we use was from C-Contour with these properties. And this is the architect of the material that we did a burn-off test to know this is the first layer, second layer roving. So what you have seen here is the roving in the middle, and the second and the first layer, and the thickness of each layer. So the geometry and the specimen that we tested, it's this one. This is the specimen that the width is 40 millimeter perpendicular to the surface, and the length is 400 millimeter from here to here, and it has a span of 340. So this part is fixed from here to here. Actually, we apply the load on the saddle and it goes through this rolling. And we're changing the C, this one, when we move it, then we can change the mixed mode ratio. So if you ask me how you introduce the mixed mode, it's here. We have the loading condition, so we can make this to a mode 1, pure mode 1, when we have pulling, and also a 3-point bending, which gives us mode 2. And when we have both together, so we have mixed mode. And in total, I did 21 tests in 4 different mixed mode ratio, and it was in displacement control with a rate of 1 millimeter per minute. So in the literature for the asymmetric crack propagation or crack initiation, there are some solutions for the isotropic material, but as you have seen here, for our case, it's not actually isotropic. First of all, it's a layered material. Each layer is also orthotropic. And in the crack tip, as you can see here, we have also fiber bridging. So the solution that it is for the isotropic, asymmetric crack propagation proposed by Professor Williams, it's based on this equation. So if I just want to summarize the equation, is like this: when you have the same bending in the crack tip, I mean if you apply M1 and M2 in a way that these two arms, they have the same bending, then you have pure mode 2. And if they are inverse and the same bending, you have pure mode 2, pure mode 1, because it opened the crack. And in our cases, so it's not easy to use this because it's not only a geometrical problem, because the material property for each layer is different and it is not isotropic. So we have changed these two to the equivalent elastic bending moment and replace the equation. So these are the two new equations that we use to separate the mode 1 and mode 2. And to verify this solution, we did some FE analysis. So here you can see the full specimen. These are the rigid part that just apply the displacement here. And you can see here that I have modeled all the layer, and also this red shows the fiber bridging that has been modeled with cohesive element. For those of you who are you know the problem for the crack propagation in the interface. When we have two different material on the two sides of the crack, they know that the solution is really sensitive to the mesh size, and it's not easy to get this solution easy. So what I have done here, I introduced a new layer, very thin layer, I call it resin layer, and the material property of this resin layer, it's the average of the upper one and the lower one. So with this one, I could get rid of the sensitivity of the mesh size. And here you can see the result for the mixed mode ratio. The dashed line is the finite element, and the solid line is the analytic solution that we have proposed. And so, as I mentioned to you, in this type of material, we have two types of actually energy release. One is due to the crack tip, and one is for the fiber bridging. So to find out the portion from the crack tip, I use the virtual crack closer technique. And for the bridging, I use the cohesive element. So here you can see that for the crack tip, it's constant. And then for the bridging zone, it is increasing until it reaches the plateau, and then it is constant. So this is the portion for mode 1, and this is the portion for mode 2. And you can see the total of the energy from the FE, that is the sum of crack tip and also the bridging, shown here by the purple line here. It is in good agreement with the experiment, with actually the analytical, the experiment that has been analyzed by the proposed analytical solution. So what we use from this investigation, so we have plotted here the values for different mode mixity. For the crack initiation, you can see here for when mode 1 is dominant, then it goes to here that mode 2 is dominant. So this is for the crack initiation, and this is for the crack propagation. And we have fitted different criteria, so power law, polynomial, or piecewise linear. And now from this equation, we are able to actually design a new joint, because now we have the failure criteria. And here it's for another path. And interestingly, here you can see that from the finite element analysis, you can see the portion of the crack tip and the bridging is changing. So when we have mode 1, we have more fiber bridging, and when we go to the mode 2, the fiber bridging effect is less. And this is, I mean, the physics is clear, because when you have mode 2, there is the sliding between the two layers, and this cuts the fiber, so there is no big fiber bridging. So to summarize and make some conclusion, we have seen that the extended global method is able to determine actually the G total, and also to make the mode mixity accurately. And introducing a resin layer and the interface help us to solve the sensitivity of the analysis to the element size. We have seen that by using exponential traction separation, we are able to model the fiber bridging, that it contributes a lot to the energy release rate for this material. And we see that with the by separation of the G tip and G bridging, that is only possible with FE model. We can see the effect of each one. And this is actually important for us, because when we are doing the fatigue experiment, the portion from the G bridging is almost gone, because when we do the cycling, it broke the fiber bridging. So that's it from my side. Thank you, and if there is any question or comment, I will be happy to.
Thank you very much.